Okay, here we are looking at variations of the underlying theme for stack, and there are varying approaches where we can use stack, most prominently in like depth first search approaches or like some sort of backtracking approaches. We'll examine four different problems. Let's have a look at the first one. 224 lead code, basic calculator flagged as hard. Implement a basic calculator to evaluate a simple expression string. The expression string may contain open and closing parentheses, the plus or minus sign, non-negative integers, so there's not another minus sign attached to an integer, and empty spaces. So the first example is an input string 1 plus 1, and the output should be the computation of 1 plus 1, 2. Example 2, 2 minus 1 plus 2 is 3. And then the third example is like the most sophisticated one with the parentheses. Open 1 plus open 4 plus 5 plus 2, close minus 3, close plus open 6 plus 8 close, and then the output would be the computation of those parentheses altogether, leading up to 23. And the note says you may assume that the given expression is always valid, and do not use the built-in function where you can use eval on a string. Next one is check if a word is valid after substitutions. We are given, so that's 1003 flagged as medium, we are given the string ABC. From any valid string v, we might split v into two pieces, x and y, such that x plus y, x concatenated with y, is equal to v. Or x or y may be empty. Then x plus abc plus y, which is the concatenation again, is also valid. So for example, s equals abc, and the example of valid strings are abc, aabcbc, abc, abc, abcc. Examples of invalid strings are abccba, so like changes in the ordering, abc, and bac. Return true if and only if the given string s is valid. And here we have like a couple of examples. Input aabcbc, output true. Explanation: we start with the valid string abc. Then we can insert another abc between a and bc, resulting in a concatenated with abc and bc, which is aabc bc. ABC, ABC, AB, ABCC. So that's like ABC is valid after consecutive insertings of ABC. Then we can insert ABC before the last letter, resulting in ABC, AB plus ABC plus C, which is ABC, ABC, AB, ABC, C. And here we got ABC, CBA, which is false because you can't insert an CBA into that one. And then C, ABC, BC is also false because it starts with a C, apparently. And some notes on the overall string length, and that your choice of letters is A, B, or C. Next one is valid parentheses. Given a string, and that's like kind of the most classical example of a stack application to just check if the combination of parentheses is valid. So that's number 20, flagged as easy. Given a string containing just the characters open and close round parentheses, and then the curly parenthesis or bracket, curly brackets, and then like the square brackets. Determine if the input string is valid. An input string is valid if 1. Open brackets must be closed by the same type of brackets. Open brackets must be closed in the correct order. Note that an empty string is also considered valid. Example 1, round, open and close bracket, true. Example 2, round, open and closed, square, open and closed, curly, open and closed, true. And then here we got like example 3, round, open, square, close, which is false, and then also we have another one, example 4. Round open, square open, round close, square close is false because the ordering is not possible. Then we got curly, example 5, curly open, square close, curly close, which is true. Now let's go to the last example. The binary search tree iterator. Implement a 173 flagged as medium. Implement an iterator over a binary search tree BST. The iterator will be initialized with the root node of a binary search tree. Curly next will return the next smallest number in the binary search tree. So here we get the example of the binary search tree, which is initialized with the correct properties of the BST, and then basically just calling next and has next are both functions that need to be implemented, and then it will basically iterate over the tree in the order such that the next smallest number is called. So we start with the overall smallest number, and then we just basically go in order through the tree, right? 3, 7, 9, 15, 20, and then we're always calling, does it still have a next neighbor? And then we return true or false. And the underlying theme for all of those problems can be solved with a stack data structure, which is what we are having a look at now. It's explained in great detail at geeksforgeeks.org, which is a computer science portal for geeks. That data structure is basically just like a stack of papers. You put another stack paper on top of that stack, and you take that paper off, and then you have like the next largest element on the stack, and then you take that off and that off and that off and that off up until the stack is empty. Or you can put up another layers of papers and take the top one off and put it back on. It is usually considered to be an LIFO, which is a last in, first out, and is basically like the antagonist of the queue data structure, which is first in, last out. So stack is last in, first out. You put it on top, and that's the first thing, the first priority to handle upon. Then they came with like some real world examples. Like my example was like just a stack of papers, but then they've got like plates stacked on top of each other in a canteen. Like the top plate is then the first plate that you will take from that stack of plates. You can't just take like a stack in the center or even the bottom one, otherwise the whole stack will like fall apart. Again, that website has like a great deal of explanations and like their own variations on the theme, so like different topics that pertain to the stack. And it also comes like with the implementation of stack here in C++ and how we can use it. You can initialize it as stack of your data structure and then push elements on top of the stack. And then we can query the top. We can query the entire size of the stack with a size. And we can take off the element of the top with stack.pop. That's basically the underlying theme that we can use for solving the problems that we have just seen. With that in mind, let's have a look at the first solution for the basic calculator, which uses a stack solution for it. And then basically the key to using the stack solution is to push your operations and your values onto the stack, and then whenever you encounter like the end of an operation, for example denoted by the end of the brackets, you just work your way through the stack on that operation and get a value from that operation, and that value you put back on the stack, which allows you to basically get nested operational structures. And then you work your way through all those individual, bracket bounded structures. And then once you work your way through, you put that value back on the stack, and that then becomes part of a larger operation, which maybe then is one value together with other values or together with other operations that you still need to work on. And that's basically exactly what's implemented here. So he's starting with a stack, and then he's just working through the stack, depending on what he's seeing in the string. So you go through the entire string, and then you feed in your stack depending on what you encounter. If it's a digit, you put your entire amount of digits onto the stack. If it's an open bracket, you also push it onto the stack, and you keep track of which sign you need to account for, like plus or minus sign. And then once you encounter that very end bracket, that's the sign where you need to start copying stuff from your stack. And that's basically all to it to do your computation. And whenever you encounter numbers, you basically do your computation with tallying your operation into a final sum, and that sum is tallied in this line here: answer plus equals s2i num times sign times the top of the stack that we have fed it in. So this one was valid substitutions in a string. Remember, with this ABC, and we can put in ABCs at various locations. And here again, we want to use a stack pattern for it, and we feed into the stack depending on what character we are getting in there. And if our character equals like a pattern on the top of the string, we increase the next element on the top of the string. Otherwise, we'll start like a new pattern thread. And if we have reached the end of our pattern ABC from our top element of the stack, we take that out of the stack. So like once we have like gone through an entire ABC sequence, which might include other ABC sequence in there, right? So like we have A, B, and then there might have been like another ABC sequence in there. Once an entire ABC sequence has been correctly worked off of, it will be removed from the string, revealing the rest of the ABC sequences that are still in there. And as soon as we find that we are not encountering that ABC pattern anymore, but maybe something like ABB or CBA or ACB, something that breaks the pattern, as we are looking into our stack, we return false. If we have worked our stack completely off and the stack is empty, then that means we have traversed our entire string correctly, and we can return true. So this one, again, is like one of the most classical examples of using a stack. Really basically just checking if I encounter an open parentheses, does it match with the closed parentheses of the same type, of the same order, etc. So here in the solution, a couple of helper functions and helper operations are first initialized. Char opposite is like find the opposite between those parentheses, so that we know which is the pair of the parentheses, which is a nice helper function. And then we got like the question if we are initiating an opening, which is key to like pushing something on the stack or needing to pop something from the stack. So if we have an opening bracket, round, square, curly, we return true, otherwise we return false. So it's a binary operation. There's like no other characters in there. It's either an open or a closing of our brackets. And then we just go through our string, and we initialize a stack of characters because we're dealing with our characters, and then go through the entire length of the string. and we go through each character and check if it's an opening. If it's an opening, put it on the stack push. Otherwise, we'll check. If the stack is already empty, that means there's a mismatch between opening and closing, return false. And then we check if our top position on the stack actually matches the current closing that we see. If we have a closing round, then we must have an opening round on the top of our stack. Remember, like as we are nesting in our parentheses on our operations, that means we always have to have like the same amount of, or like the same type of brackets there. So if we have curly and curly, that's good. But if we have curly and round, then that means there's again another mismatch. And that mismatch is the mismatch of type and not the mismatch of open and close. So if that happens, we also return false. Otherwise, if we found a pair, pop it from the stack. And then check what's the next amount of brackets going on there up until we hopefully have exactly pushed and popped the same amount of brackets on the stack, with them all being matching each other as pairs. And then once they do, we can return true, which is at that point in the code. A binary search tree, right? And go through that search tree. What was it in order, right? Can also be implemented using a stack, right? So let's see where we have our stack. It's initialize this stack tree node as in the very first line here, right? And so that's like our data structure. It's a stack of tree nodes, right? So we would know if the tree node has a child. And so whenever we add an element to the tree, we also keep track of that in our stack. So it's like kind of key to it. We're pushing that element onto our stack here as push root. Then the key thing is like finding the next smallest number. Basically goes through the stack here, saying give me the small tree node as top. Pop it from the stack. If small has a right neighbor, we need to add that element again to the stack. And then we return that value. If it doesn't have a right neighbor, we straight return the smallest value, because if it has a right neighbor, then that means we still have elements that are greater in value. And that's basically also key to the thing where we have the stack has next operation calls if still something is in the stack. If the stack is not empty, that means we still have like another element on the stack that can be considered the next smallest element. So that's basically all to it, right? So we're starting with our iterator, putting that onto our stack, and then we work our way through as we pop an element from the stack, and then check if it still has like a right neighbor to it. And we put that element on the stack as well. And if we don't have any right neighbors anymore, then we basically check if there are other elements on the stack already, which are higher up in the hierarchy of our tree. Right? And then the lowest element on the stack would have been like the root element of the tree. And going right and right and right, we would then find the next smallest element. And has next, again, returns if it's empty or not empty.